Hey everybody! In this video, we're going to kind of review the topics we've learned so far related to functions and go into compilation and execution and why we even use functions in more detail. If we head over to the notes, we'll see that there actually isn't a warm-up task. I don't know if that is sad or thrilling that we're not going to be writing any code in this video. We're just going to be going through these notes and kind of having a conversation about how program compilation and execution works with functions. And then we're going to talk about why we use functions, because you might be looking at code like this or code like our GPA computation fun and saying, okay, I hear what she's saying about these functions being reusable and whatnot, but it seems like the code got longer in some ways. Like, we could figure out if 3 and 10 are even much shorter than having to write all of this function definition stuff and this function call stuff. I hear you. So we're going to spend a devoted amount of time in this video to talking about why we use functions. And hopefully at the end, I will have convinced you. All right, let's first talk about how programs are compiled. Many videos ago, we drew a large diagram on the whiteboard that talked about how compilers translate source code into object files, and those object files are linked with other object files, specifically object files from code we didn't write, so that we can have one executable file that contains all of the machine code necessary to execute our program. Well, none of that's going to change with functions. But we do need to talk more about the nitty-gritty details about how the compiler translates or parses our code. So, when the compiler encounters a function definition, it notes the existence of the function but does not execute the function. We know this. We know that we have to call a function in order to execute it. But does it matter when the compiler encounters a function definition? Yes, it does. We've been putting all of our function definitions before main, as in this example here. Check if even is before main, because the compiler starts at the top of your code and compiles from top to bottom. So as it's processing our file, when it encounters the definition for check if even, it doesn't execute this code. It just makes a note of it and says, okay, check if even accepts one argument and it's an int and it returns a bool. Got it. Now, anywhere after this header, where it gets all the information it needs to know in order to compile code that calls this function, the compiler is okay with code occurring that calls this function. So that's why this definition is above main, because main has a call to check if even. At the end of a function, the compiler inserts a statement that essentially transfers control back to the caller. So at the end of check if even, we return is even. How does the compiler know to go back to main? Well, it inserts a statement such that when the program executes, there's essentially a jump or a branch statement that says, okay, main was the function that called this function. Here's the exact line that you need to go back to. We can call check if even from other functions. It doesn't have to be from main. The compiler will keep track of where to go at the end of check even based on what function called check even this iteration. All right, so now that we've talked about how the compiler compiles programs that have functions, let's just review how execution occurs with a program that has functions. Execution always starts with main, and the body of main is executed sequentially from top to bottom. When a function call is encountered, the execution in that function pauses and the flow of execution alters, and it shifts from main, or from that function, to the body of the function that's being called. After the called function finishes executing, then the function that called this function, which in this case is main, continues with the next statement after the function call. So it continues sequentially. Our code is sequential until we encounter a function call, and then we might jump somewhere else in the code depending on where that function definition is in the code. One note here, functions can call other functions. We've actually been doing this all along. Like, for example, we will have inside of our main definition a call to POW, or we might have in our main definition a call to a function that we wrote. Well, we can also call functions we wrote from functions we wrote. So really, once you define a function and the compiler knows about it, you can call that function anywhere below that definition. And we also call functions from libraries. We just need to include the library, and then the compiler knows about the functions so that if we go to call them, it's not going to give us an error. All right, so that was kind of a review of compilation and execution, because functions can make things seem a little tricky when we've got some jumping around in our code. Now, why use functions? I've got lots of reasons here. First, top-down design, breaking a large, complex solution into small, more manageable, more solvable logical units. This is actually called modular programming, where you break your program into modules. This can help in terms of teamwork and collaboration as well. The stereotype that the software engineer sits alone by his or herself in a dark cave just coding away all day long, that doesn't happen, or if it does, it's very, very rarely. Typically, you'll be part of a large software engineering team where many of you, let's say 10, are all working on the same source code. So you would likely architect your program such that it's very modular. All of the functions related to this are in this file, and all the functions related to this are in this file. That way, you and your teammates can be working on different parts of the code at the same time because you have a well-architected modular design. Our next reason, procedural abstraction. This sounds like a fancy term, but it's really not that fancy. What it means is you can treat a function like a black box. You don't need to know what's inside the black box in order to use it. As long as you know the inputs and the outputs of a function, you can call it. For example, I've actually drawn check if even as a black box here. We know that it accepts an integer input called num, and we know that it produces a true false. We don't actually need to know the details of how check if even is implemented in order to use this function. We do this all the time. We don't know how POW is implemented. We've never seen the source code for it. We've never seen the source code for any of those functions related to files like isOpen, good, EOF, fail, open, etc. We treat them like black boxes. We know the contract that we need to adhere to in order to call them. That's what's the name, what's the input, what's the output, and then we can use them. And this is really nice. If we had to learn all of the details of the functions before we could use them, we wouldn't be as far as we are in this course because we would still probably be bogged down way back with getLine. It would be crazy. Reuse, I think this one's pretty self-explanatory. When you write a function, you can reuse it multiple times. And I don't just mean in this program, right? You could reuse your code in another program. In fact, we're going to learn how to write our own libraries so that we can do that. Reuse is so important, especially for functions that perform mathematical computations. I know I keep using POW as an example, but it's one that we use often. Maybe I'll use square root. Let's use square root, for example. All over the world, people reuse the square root function in the CMath library all the time. We, as computer scientists, perhaps don't want to spend the time to implement our own square root function. And it might be maybe kind of buggy because maybe we don't know all the corner cases, or it might be kind of slow because we haven't written it to be very optimal. But the square root function in the CMath library meets all of those standards. It's not buggy and it's fast. So that's why we want to reuse it. Let someone else write the code and then test it, make sure it's been validated, and then we can reuse it over and over and over again. If there are enough functions with high reusability and high cohesion, meaning they are similar and they work well together, you'll typically put them in a library like CMath. And the definition for a library then is a collection of functions. Just putting it all together so that you can package it up and distribute it to people to reuse. Testing will be the last reason that I'll give for why use functions, but I'm sure as you gain experience in programming, you'll be able to come up with some more reasons for using functions beyond these. These are just the big ones. Testing. With top-down design and modular programming, you can think of each function as its own little program. That program has inputs and it produces outputs or causes some kind of side effect like a state change in the program. And since it's a black box, and we could treat it like a black box, we can test it like a black box, meaning we can pass in a bunch of different inputs and test to make sure that for each input, we get the correct output. If we test each function independently, and we know that the function is correct for all possible inputs, which is actually surprisingly hard to do, once we know that our function is bug-free, we can integrate that function into a repository of other bug-free functions, and then we just have to test the integration. We don't have to retest the individual functions. Then as we start to integrate and integrate and integrate into a really large software system, if we encounter a bug, we know that it's due to integration instead of due to a function. Or maybe our function wasn't as bug-free as we thought because we didn't write test cases that fully covered all possible combinations of circumstances and state. Then we'll find out later that the bug might have been in one of our functions we already tested, and then we can improve our testing. But really, the idea is test the little tiny individual submodules independently. Once those are all correct, then you can integrate them and test each time you integrate. Here's a little bit more on modular programming. So modular programming is where we write our code to have small, independent, interchangeable modules. Specifically, the modules that we've been working with in C++ are called functions. But there are other types of modules that you'll learn about as you continue on in programming. So there's two things related to our functions or our modules that we want to strive for, cohesion and loosely coupled. Cohesion is a measure of how related and focused the functionality is within a single unit. So we want our functions and our programs to be highly cohesive. This means that a function only solves one problem. It's very focused. For example, we probably wouldn't want to write a function that both computes the GPA and displays the GPA because that's not a very highly cohesive function. It's solving two different problems where we know we want our functions to solve one problem or one task. Highly cohesive functions and programs are more readable, testable, reusable, understandable, and maintainable. And as you continue programming throughout your career, you'll start to see all of these features come into play, especially the maintainable part. You'll often write code as part of a software engineering team that once you finish the project and deploy it to customers, does not mean you are done with that code. The customers will find bugs and they'll report those back to you, or they'll request additional features, and you'll be maintaining that code for a long time. Or maybe you'll be put on a project where you'll be maintaining code that you didn't originally write. That's why the more cohesive your functions are, the better. Lastly, functions should be loosely coupled, which means that functions are not dependent on one another. We want to write our code such that it's highly reusable. In order to do that, our functions have to be independent modules. In general, if we can write highly cohesive and loosely coupled modules in our programs, we're going to be writing really well architected modular design programs. And here are some of the benefits of that. Reducing the length of a program and promoting more efficient debugging. And this part right here is actually really important. It can take a long time to trace down a bug. So if your code is well written to begin with, this time to trace down a bug will or should take less time. And then you can spend more time on the design and testing, which is arguably more fun than debugging a program. Okay, so we saw a definition of a library, a collection of functions. We've been using a lot of libraries already. We always use IOStream in order to get user input and output with cin and cout. We've also used cmath for math functions like pow, square root, absolute value, etc. cstdlib for rand and srand. Any others that you can think of? We've been using ctime, for example, in order to get the time function. fstream as well for dealing with ifstream and ofstream variables. So I've kind of already mentioned how important the cmath library is so that we can reuse already tested, well-implemented math functions in our code. We don't have to know exactly how the math functions are implemented in order to use them. We could treat them like a black box. So here's some header-like information for some common cmath library functions that you may want to use in your program. At a high level, this is all the information you need to know in order to call the function. You may want to read documentation about each one of these functions before you use it, just to make sure you know about any assumptions or side effects that may occur as a result of calling this function. For example, one thing to note, looking at cosine, sine, and tangent, they accept doubles, but it's not clear based on this information alone if that double value is in degrees or radians. So you'll want to read the documentation to find out. And I'll tell you now that these functions expect arguments to be in radians, not degrees. So you would have to do a conversion process yourself to convert degrees to radians in order to pass in radians when you call one of these functions. So hopefully at the end of this video, you are a little more convinced about why we use functions. As our programs start to get larger and larger, all of these topics like modular programming, top-down design, functional decomposition, structured charts, they'll all start to make more sense. Just hang in there, keep practicing your coding, and if you're feeling a little unsure about functions, I would probably take some time now and practice some functions, resolve some of our previous programming assignments using functions before you move on.